Well, hello everyone. This is Jeff Eisenman with Maverick Applied Science. Today we're going to have our third webinar of our webinar series here at Maverick Applied Science. This follows the first webinar by Tom Haber that we did on FRP repairs. And then last month, Daryl McCulloch, our engineering manager, did one on pipe stress analysis. So today, basically, I'm going to be presenting a case history on some material testing we did on a piece of FRP piping from a sulfuric acid system. So we still have some people streaming in now, and so we're probably going to wait about 2 more minutes, and then we'll get started. All right, looks like everybody's here that's going to be here. So we're going to go ahead and get started now. So this is a presentation, as I mentioned, on sulfuric acid piping. I did this inspection with one of our inspectors back in about 2013. Was the first time that we saw this system. And the picture on the left-hand side here on the title slide is kind of what it looked like at that time. So let's go ahead and get into it now. So here's a little bit about me. I founded Maverick Applied Science in 1999 as an independent FRP engineering company. Since that time, we've grown over the past 21 years and now offer non-metallic engineering services for FRP, dual laminates, thermoplastic materials, pipe supports for those systems, as well as inspection services. In addition to our design capabilities, our engineering responsibilities have involved acting as the owner's liaison for engineering construction assistance, including bid reviews, calc design reviews, for basically adherence to project specifications and industry codes and standards. We'll probably touch on codes and standards a little bit here in a second. In addition, we also do quite a bit of in-shop fabrication inspections, as well as in-plant outage maintenance assessments and failure investigations. I'm currently a member of the ASME Board of Pressure Technology Codes and Standards, as well as a member of the RTP1 main committee and the ASME RTP1 fabrication subcommittee. And currently I'm the new chair of the ASME non-metallic pressure piping systems NM2 subcommittee standard for FRP piping. So that's a lot about me, maybe more than you wanted to know. So a little bit about this webinar. So we do encourage questions, so feel free to ask questions. We'll be in chat mode for the most part. So you'll see on your control panel, you'll see the questions drop down. You can type your question in the box below, and keep in mind that all questions are private and will be between you and me or the organizer. There's no chatting in between attendees, so nobody else will be seeing your questions except for the organizer. So when we install a new system, we always want to maximize reliable life of process piping. So this is kind of a sort of a recipe of how to do that from the start. So we always want to have, you know, good up-to-date standards. We want to specify the best materials. We want to work with good manufacturers that have good qualified technical support. You want to see detailed engineering, particularly in piping. And then we want to have QC and QA throughout the process. That's QC at the engineering phase. We want to see QC in the shop, and then we want to have QA in the shop. And then once we get into the field during the construction phase, QA, site QA is important as well. So that's what we do at the beginning. So, but then, you know, later on, you know, we always get the question, well, okay, well, how long is it going to last? You know, when do I need to start to worry? So that's largely what we're going to talk about today. So, as I mentioned, we did this inspection in around 2013. At that time, it was 18 years old. So this was around for quite a while. As you can see, it looks pretty bad. A lot of discoloration. So you know, as the owner, you know, he's got in his mind, okay, do I need to replace it now? Are more problems, you know, on the way? You can see it looks a bit like a zebra. So you can see where you see the if we're looking at the picture on the left-hand side, the kind of the amber colors here are probably butt joints. The darker colors are straight pipe, or where the thinnest areas we'll say are. And you can see we've got some elements that are actually starting to show on the outside, where you're getting contamination to the outside. Interesting, if you look a little closer, you can see some of the joints, and you can see the joints are thicker, so they're amber, and you'll see these fine lines in between. Kind of looks like a zebra. So that fine line is actually the butt joint, the gap between where the two pipes are meeting. When we did this inspection, generally we found that the Barcalls were approaching you know, upper 40s to 50, which is not really surprising for something of this age. You would expect to be pretty cured after almost 20 years. And looking at the photos here, I'll stick with the photo in the middle here or to the left. This is piping which is upstream of the plate heat exchanger, which you actually see here in the picture on the kind of left side of the left photo. Is the plate heat exchanger. So the process on this side ran about 185 degrees Fahrenheit. If I bring your eyes over to the right-hand side of the screen, you'll see that these pipes look much newer. They're largely, you know, to a good extent, still amber in color, and these are actually downstream of the plate heat exchanger, and generally are running at about 120 to 130. So you can see temperature has a significant influence on the performance and the life of the piping. So when they asked, you know, how do we, know how much longer this is going to last, we said, well, can we take a spool out of service and do some testing on it? So they sent us a spool. This is one of the spools that they sent us. So this is, I think, around the 6-inch piece of pipe, maybe I think it's 8-inch actually. And unfortunately, it wasn't the very first spool. The first spool we had was much darker. And here's some samples from that. Actually, what happened was we actually cut samples before we took a picture of the sample, and then they put the sample outside of the lab, and it was still in this brand new nice oak crate. Came back the next morning, and the crate and all the remnants of the sample were gone. So I guess somebody really liked that oak crate. So, the photos here that you see, you can see on the left-hand side, this is the corrosion barrier. So you can see somebody described this as a dried up riverbed. You can see some cracking of the corrosion barrier. I'll show you that this is going down into the bale layers, and then on the other side you can see some of the darkness in the this was one of the flanges where we cut out a piece as well. Generally, this system was as I mentioned, a regenerative sulfuric acid service, and generally ran as weak acid between 10 to 15% concentration. So we're going to look down a little bit further. So here's our sample again. So now what you see here is, so here's a close-up, so you can kind of see that cracking in the corrosion barrier. You can see the cross-section of the structure down underneath here. Looks pretty clear for the most part. Don't see a whole lot of contamination. Compared to other acid surfaces, we haven't found that we get a lot of contamination and permeation into the structure of the laminates. One interesting point is you'll see the joint line here where actually this is the elbow and the straight pipe meet, and you'll kind of see that kind of ruffled line in between there. We found that this, or at least believe this to be basically the resin coating on the end of the pipe. So it kind of gives you an idea of what that looks like after almost 20 years. It actually nearly separated, at least for the depth of the corrosion barrier, but is still kind of remnant in the joint space. So moving on. So now we're going to get into some SEM. So this is spectral electron microscopy. And so in this slide, what you can see is basically a cross section of this joint. You see basically when we take the sample, we basically immerse it in epoxy potting compound that kind of keeps the sample stable. So when you start to cut slices, it doesn't fracture and break up into small pieces. But looking a little bit closer, so you can kind of see basically the boundary of the corrosion barrier here, and where you see the areas here, this is where the cracks and crevices are that you saw on the surface of the corrosion barrier. Largely, this is, as you can kind of see, this is going down into the veil layer. You can see here that there's that seal here, and then the opposite side where it started to come off from that. I guess that's kind of the elbow side there. So looking a little bit closer, here's a close-up of that of that joint area here. So you can see the potting compound coming down, and you can see basically the voids in the corrosion barrier where you can see the cracks. You can see where there was glass and now there's not. We're going to talk some more about that. You know, given the age of the pipe, this isn't really bad. As it looks pretty rugged, or ragged maybe is a better word. But if you look at basically the condition of the structure and the corrosion barrier further in, it's still actually you know, somewhat serviceable. It's not totally toasted. Here's another picture looking further down. You can start to see basically kind of at the base of the joint there, and you can start to see where the chemicals are starting to come in and kind of migrate into the corrosion barrier further, and it's starting to get into the glass and starting to break down the resin matrix here. So let's talk about the chemical attack. So here's some more SEM, and so you see the green line that we have here on the left. So this more or less kind of defines the boundary between the veil layer, which you see you know, pointing to the top here, largely going to be what would have been a glass veil. At this time, you know, more than 90% resin probably. And then from, you know, below the green line, this is where you're getting into your chopped strand mat layers. So you can start to see kind of what's happening there as well. If you look at the right-hand side of the slide here, this is a close-up of the chopped strand mat area. So what you're looking at here, where you see all the black circles, that's where glass was. That's where basically our chopped strand mat layers were. And basically, this is e-glass. It's again, this is going back to the late 90s. So ECR wasn't prominent at that time. I want to say around 95 or so is when Owens Corning came out with that, but it really wasn't used until probably close to 2000 on more of a regular basis. So this is e-glass, so you can see that the sulfuric acid has attacked it. It's leached out the elements, and it leaves these conduits behind where the glass was. Though you can see the white circles here are where the e-glass is still intact. And you can see kind of these oblong ovals here. So this is actually your woven roving layer. So you can see basically where your chop is coming down here, and then where you start to hit. This is probably, you know, your first couple mats in your structure, and then you can see you're seeing your alternating woven and mat going forward there. So kind of give you a feel of what the what the construction is and kind of what part of the laminate you're looking at. So we get quite a bit from this. We're starting to understand what kind of what's happened to this and what the condition is. Here's another close-up. And you can see very clearly here, so you can see the voids where the glass is totally gone, and then below that you can start to see here's individual glass filaments where you see the kind of the dark gray around the edges here. So this is basically where the glass is beginning to be attacked. So the white is more or less you know, fresh, pristine glass, not fresh, but unaffected, we'll say. And then these dark areas that you see are where the glass is beginning to degrade. It's being attacked. It's what we find is that some of the elements get leached out of the glass and start to break it down. And then you can see where crevices between the glasses are starting to occur. And then, you know, further down, these are, you know, largely more unaffected parts down here as well. You know, on the right-hand side of the slide here, you can see you know, more of where the glass has been attacked or completely degraded, and then you can kind of see a close-up of the cracks that are beginning to form, you know, throughout the this resin matrix area. So energy dispersive X-ray spectroscopy, EDS. This is another one of our tools that we can do in an examination of destructive testing. So what you see here, if you look at the left part of the slide, so you see spectrum 1. So this is basically, we took a sampling at this location. So as you can see the crevices in the surface of the veil here. So we're right at near the surface of the corrosion barrier. And then looking to the right-hand side, this is the scan of that area. So this shows all the elements that we're picking up in that area, and also the magnitude of those. So you see carbon, which we find in almost everything, oxygen, copper, which probably comes from some of the resin additives, sodium, silica is the glass, and over here is sulfur. You see chlorine and calcium as well. But we're most interested in sulfur, so we can actually measure the degree of sulfur that is present at that specific location. So then we actually took 5 locations and samplings from this laminate. So we're going to look a little bit further down, just so you see spectrum 3. And so again, you're seeing, you know, more carbon, oxygen, chlorine, silica, and then you see the sulfur over here, and it's greatly diminished. It's basically trace elements at this point. And this is really about the into the sulfur. So, you know, at this point, we've got our veil layer is approximately 10 mils. We're about another 10 mils down. And generally what we found was between 20 and 30 mils deep into the corrosion barrier is where this, where to the extent that this it permeated into the laminate. So to kind of give you a perspective, our typical corrosion barrier, you know, is 100 mils thick and we're 30 mils into it, say. So really we're only a third into it after almost 20 years. So really not too bad for sulfuric acid service, particularly at a fairly hot temperature. So we've talked about SEM, we've talked about EDS. These are very, you know, quantitative measurements for this. One thing that was kind of interesting from all this, you can see all the discoloration and some of it looks pretty bad. And going into this, we expected that was going to be sulfur. You've seen sulfur when it's burnt like this, it kind of gives you that brown tone. And when we actually did the elemental breakdown, we found that what was on the surface was not sulfur, but in actuality it was iron, and that had actually migrated to the surface, obviously through some of these conduits that the glass afforded for it later on. And going back to the process operators, we found that there was a kiln, because this is a regenerative process, so kind of like a recycler. They had a hot kiln that was basically steel upstream of the scrubber and this is just coming out of the quench unit within this scrubber system. And it was basically carrying iron from the kiln, and actually it was collecting and depositing on the surface of the laminate here. So that was kind of an interesting find. We actually went back and confirmed that a second time, because it just didn't make sense the first time. So we thought, well, maybe something was an error, but in actuality, that is iron that you see is the dark discolorations here. So that's a little bit about that. So looking at permeation, so this is basically a EDS line scan, actually tracking sulfur content through the thickness of the corrosion barrier. So you see at the very top of the left-hand side photo, the top is basically the inner surface of the corrosion barrier, so you can kind of see the potting compound at the very top, that dark area, and then basically that's where our line scan picks up, and then so you can see basically the line scan is superimposed over this image, and you can see that at the top we're showing a lot of sulfur content, and then as we're getting down into the thickness of the corrosion barrier, it's diminishing substantially to the point to where it's quite negligible. You can see just at the very bottom of this, it's hitting the structure, is what that is. You see kind of the first probably layer of woven roving there at the very bottom of the image. So we can actually get a pretty good, obviously this is just kind of one location, but we get a pretty good picture of what the real permeation is, and as well as kind of the condition that has caused. So one of the other things that we can do when we have a sample that we can actually do some destructive testing is we can confirm the resin. So as I said, this was 18 years ago when this was built, or well, at this time it's probably more like 22 years or so now, 23. So today there are actually resins out there where you can actually get a 100% confirmation of the actual type of resin it is, down to the exact model number pretty much. But going back into the 90s, that wasn't really the case. So what you see here is basically, we basically did a infrared scan, and the lines here are basically, you see the internal resin. The outer resin would be probably this is non-discolored, so that would be furthest to the outside, and you see the black outer resin, and then you also see this discolored part, and you see yellow resin. So basically what this is telling us, they're all, I mean, they're not perfectly overlaying, but largely following the same signal on the waveform. So that basically tells us that the resin is the same throughout. The corrosion barrier resin is the same as the structural resin. And if we knew what it was in before, we could also go to the resin company and ask for this data and overlay, and you could compare, and it would tell you, in our experience, better than about 95 to 97% that you can identify that it's agreeable or it's not. If it wasn't, you would see an odd spike that would be in the middle of this that wouldn't match up. But in most cases, we find that it overlays pretty much what you see here. So we feel that that's pretty good confirmation of the resin when we see that. So to kind of circle back, what we've been able to do here is readily identify the condition of the pipe, and what's different from a standard inspection is that this is an analytical report. It's reproducible, it's factual, it's not just opinions, and we've been able to basically assess what the level of permeation is and the condition of the pipe. And in this case, we've done this, I think, 3 times for this owner, about every 2 years. And that system, which they were concerned back in 2013 that they needed to replace it, is largely still in service. Some of the worst areas are they have chose to change out, but I would say right now 3/4 of that system is still in service, so that they feel really good about that. We were able to give them a very definitive report and the level of confidence that the operators can take their management and tell them why they believe that the system is still serviceable, and they have some documentation to prove it. So that's largely what you're getting out of this process. So again, some closing thoughts. This is laboratory testing of in-service piping. So basically what we did was we said, okay, in your next outage, or a lot of these plants will have many outages where they'll be down for a day or two. They'll fabricate one spool on the side, and then they have this little mini outage, and they'll drop one piece out, they'll put another piece in, and they're back up and running in a day, right on schedule. But then at that point, they can send that spool off to us, and we can do our thing. We can examine it, we can cut it up, we can do all the scans and everything else that we need to do, and we can give them a real good assessment of the condition of the pipe, far more than what we can actually do even with our in-field inspections during outages. And they've done this basically more or less while they're in operation, with little to no interruptions, and they're getting a verifiable and basically a repeatable result that we put in the form of a technical report. And it gives them a high level of certainty and confidence. You're not just relying on the experience of an inspector and the quality of the company that's doing the inspection. you have basically a solid document that you can take to your management, and that you can stand behind, and gives you a better feeling that you're not overextending yourself, or having to worry about, is this going to hold up, or do I need to replace it now, and ask for that that big budget to replace the whole system. So it's it's very qualifiable. It's good science. There's it's all pretty much black and white. We try to do the reports where everybody can see it, and then we can talk about it if there's questions. And generally, the results are pretty good. So that's kind of where I want to leave you for today. So again, this is Fiscal Testing. So we're not always able to do this on every system, but where we can drop a spool out, this is a very good tool. It helps to give the operators a very good picture of where they're at, what they're dealing with, where their concerns lie. So this is definitely something as an operator for you to kind of keep in the back of your mind as a good option going forward. So one thing I wanted to mention too is this is our third monthly webinar. Next month, about this same time, we're going to be doing another one. We're going to try to do something a little bit different. We're going to do an expert panel discussion. We've done these quite a few times at our FRP forums that we would generally do annually. Unfortunately, this year we weren't able to do that due to Corona. So we're going to kind of change it up, and we're going to do one on FRP reliability and materials. So we'll start off with a few slides to kind of open it up, and then we're actually going to open it up to questions and try to stimulate an open discussion of questions and answers between us and y'all. So keep an eye out for that, and hopefully you have a chance to see that as well. And that's all I have for today. So Tom, I think this might be a good time for some questions.
Okay, sounds good, Jeff. One of the first questions we got was, you discussed Barcoll early in the presentation, and someone asked, what was Barcoll hardness and how do you take representative samples of that?
Okay, so so for FRP, we have a Barcall compressor. It's kind of a pistol device that basically it has a hand grip, has a dial indicator on the top, kind of like a dial feeler gauge, more or less, and it has a hard pin with a spring on it at the bottom. So basically, you take this pistol grip and you basically put pressure on the pipe. You lean on the pipe. Generally, we like to do on the corrosion barriers of new pipe. And basically, what it does, it reads the hardness of the pipe at that location. There's an ASTM standard for this. Generally, you would take, I believe it's 10 samples in a localized area. So you would take 10 readings, and then generally you would say throughout the high and the low, and average those, say 6 or 8 in between. And that would be your Barcoll hardness. For most FRP laminates, we find that depending on the resin, as well as depending on the veil, C veil will give you better Barcolls, higher Barcolls than say a Nexus veil. Generally, they will lie pretty regularly between about 30 and 45. 30 might be something with a Nexus veil. 45 is probably a harder resin, something like one of the Novalax might read a little bit higher, something like that.
Okay, sounds good. There was a couple of questions that were asked if you knew the concentration of the sulfuric acid that was in the piping. I think you talked about that at one point.
Yeah, this was weak acid, so generally the concentration varied between about 10 and 15% acid. So that was the concentration. And again, the worst area is operated at about 185 degrees Fahrenheit.
Okay. Another question was, is it possible to use this similar type of sampling and testing protocol on a vessel? Could you use this with, say, cutout samples or core samples from a vessel?
You could. We've actually done this with like manways. If you have manways or like an inspection port cover where you just have just a blind flange, you can take those off, swap them out, and do a very simpler thing. It's not quite the same as the shell, as those parts would be hand layup, but the corrosion barrier is going to be the same, the exposure is going to be the same. So you could do core samples. If it's really important, you can do core samples. Don't always like to cut a hole in a good tank. But in most cases, they can be repaired. You have to kind of think about what the service is, and how severe it is. If it's, ammonium chloride, then it's probably not a big deal. If we're talking, hydrochloric acid, which has a lot of permeation and contamination in the laminates over time, we might not want to cut that because it's harder to bond on a contaminated surface over time. So, definitely, inspection port covers and manway covers and things like that are really easy to do something like that.
Okay. Another good question that came in, maybe a way to explain things and relate it to metals, is does the corrosion barrier that you're speaking of equal a corrosion allowance?
Um, I would say no, it doesn't. I mean, it's in some ways it does, in that we look at the corrosion barrier as non-structural. So we don't put that into the calculation, in the structural calculations, on how thick say the pipe or the tank shell should be. So from that standpoint, it's not part of the structure. But it doesn't necessarily all go away either. Like I showed you here, we have a 100 mil corrosion barrier that was put into the pipe, but the permeation of it, which would be more like your corrosion allowance, was only 30 mils deep. So that's kind of the difference. In some surfaces, obviously sulfuric acid is a fairly severe surface, not necessarily the most severe, but a fairly severe one. So we see some degradation and some permeation. In other surfaces, it's almost negligible. You won't see that cracking. You'll see very minimal permeation. You'll get very good hardnesses on the inside still, and the integrity and even the hardness of the corrosion barrier will be there to a great extent. So it's very surface specific on how much you'll lose in that corrosion barrier. So it's a similar concept, but not exactly.
Okay. We had a follow-up question, Jeff, about Barcoll testing that I thought you could probably resolve pretty quick here. The question is, does the Barcoll hardness change for different materials like FRP and other thermoplastics?
Oh, totally. I mean, if you look at just so I'll say every material has a different hardness, whether it's a thermoplastic, a thermoset like FRP, or metals. If you look at metals, I mean, you have different hardnesses from, say, aluminum to carbon steel to titanium. Within plastics, it's the same way, and within FRP, it's the same way. Just a broad, discussion to say we have 8 different resins, and each resin may have a slightly different Barcoll. Or at least within the families, the Barcolls will be different. And as I mentioned, they can range from something close to 30 to up to 45, or you could even approach 50 depending on how it was cured. So one resin will definitely have a different Barcoll than another resin, depending on its kind of, I guess, how it's made.
Okay, very good. Another question came through where someone was asking about whether filament wound pipe and contact molded pipe would see differences in service like this. The questioner asked about filament wound piping because it looked like some of the piping in the presentation was filament wound.
I believe some of the piping is filament wound in this system. You see a lot of hand layup fittings in it as well. Generally what we find is the corrosion barriers are pretty much made the same, whether it's filament wound or hand layup piping. So from that standpoint, there's not really a difference in the integrity or the construction of the corrosion barrier. What we do see is that there is definitely an influence in permeation with respect to pressure and non-pressure. So basically what I'm getting to is, we may see more permeation and more aggressive service in a pressure piping application than say a static storage tank application. So we could have the same materials in both, and we may see more degradation in the piping than the tank itself, because the tank is largely static. It's not, the pressure actually will push the fluid contents, the molecules into the surface of the corrosion barrier, where you don't really see that in, say, like a static, atmospheric storage tank. I'd say that's probably more of a difference than from, method of construction.
Okay, very good, thank you. Another question came about capping the cut edges of piping before they're installed, before they're assembled. Is that a good idea?
At times it is. I wouldn't say always. I mean, this was this was basically resin capped in a sulfuric acid surfaces, which is probably a little more severe than average, but yet it at this point it operated for 18 years with no issues. We weren't seeing breakdowns of the joints, didn't see huge contamination and deterioration of the edges of the joint, and then the cross sections that you showed, pretty much the edges were clean cuts. I've seen the same pipe in hydrochloric acid service, for example, and you would see substantial deterioration and staining in that cut edge going back 1 or 2 inches maybe. So as I mentioned earlier, HCl is a much smaller molecule, so it's able to permeate more, and at high temperatures it can be very aggressive. So for this service, I can't say resin capping was a bad thing. For something like HCl or chlorine dioxide service, something like that, which we know are much more aggressive surfaces, probably capping them with a with a couple mats and a veil, full corrosion barrier end cap is probably more appropriate there. If it's some kind of mild service, just seawater or something like that, resin capping is still desirable, but it probably would not be hugely detrimental if you did not do it. So, but I would still want to see it. But from a practical standpoint, it's very service specific, so you have to kind of think about that, because it is a level of effort that you have to add to it if you're going to end cap a pipe.
Okay. Very good. We had another question about erosion. The question was, what can be done to investigate erosion instead of chemical permeation as shown in this presentation?
Well, and actually, and with this testing, we can largely do the same thing and look at erosion. I mean, keep in mind we have a physical sample, so we're splitting it open, we're examining the corrosion barriers. Taking samples, you can actually measure, the remaining corrosion barrier or erosion barrier in the pipe. You can see where the wear is around the joints and the elbows, for example, is where we generally see the most of it. So we've done this at the same program at a power plant that has FGD slurry piping for at least 2 or 3 times also. And it's the same thing as, we can't stick our head in the pipe. How do we know when it's going to wear out? So we'll have them drop a spool out every probably other year, and we'll look at erosion concerns for that and get a feel for what the condition of the remaining corrosion barrier is. Depending on the service, we find some of them are almost perfect, where you can still see the lines from the Mylar molds when it was actually built, and other times in certain specific locations, you can see that there's substantial wear where there's higher velocities. Maybe we find gypsum services a little bit more demanding than limestone slurry service. And then as another tool, when we're looking at the erosion side, if we can get it in outage, we would prefer to actually look at it with the borescope and actually take the borescope into the piping, and then we're taking video and basically examining a lot more of the piping than just one spool dropout. But to do a sampling in between those periods, this testing would work well for that application as well.
Sounds good. Really, that's the majority of the questions, Jeff. There are a few that are relatively detailed that you should probably answer with a phone call or online, but otherwise, the only remaining real questions were, will the webinar be recorded, and will people be given access to it?
So yes, the webinar will be recorded. We'll be sending a link out, I believe is what we did for everybody who attended, if you want to share it with a colleague or something like that. Also, within a week or two, we're going to post it online, so it will be up there much longer. If you want, you can find it there. If we will probably be touching base with everybody to send you that link, as well as kind of get your feel for get some feedback on the webinar. If there are questions that we weren't able to answer, or if you have more that you think of later, feel free to reach out to me. If there are more detailed questions that maybe we have time for today, I'll be touching base and either sending an email to follow up, or maybe a phone call if that makes more sense. So appreciate everybody for attending. As I mentioned earlier, we're going to have another one of these next time in a month, and that will be a broader panel session. So we'll have more opportunities to have more questions at that time. So thanks a lot, everybody.